Welcome to the QUASARIA channel. Today we will go to one of the most mysterious and frightening places in our universe, the giant void in the constellation Coma Berenices. Imagine emptiness, an absolute, cosmic void 1.3 billion light-years across. To understand this scale, let's remember, light travels the distance from the Earth to the Moon in a little more than a second, to the Sun in 8 minutes. Now imagine the distance that light travels in a billion years, and multiply that by 1.3. This is the giant void. Voids are not just empty patches of space. These are giant bubbles in the cosmic structure of the universe, practically devoid of galaxies and stars. If you think of the universe as a sponge, voids are air bubbles inside it, and matter is distributed along the walls of these bubbles, forming filaments and clusters of galaxies. The giant void in the constellation Coma Berenices is one of the largest voids known to us. It was discovered in the process of large-scale mapping of the universe, when astronomers began to notice strange patterns in the distribution of galaxies. Where there should have been thousands, if not millions, of galaxies, there was an almost absolute emptiness. What is happening inside this cosmic abyss? Contrary to what one might think, the voids are not completely empty. There are still individual galaxies in them, but their density is incredibly low, hundreds and thousands of times less than in ordinary regions of space. These are lone galaxies, drifting in an unimaginable void, separated from each other by distances that pale even the intergalactic expanse in comparison. The formation of voids is associated with the earliest moments of the existence of the universe. After the Big Bang, matter was not evenly distributed. Quantum fluctuations created regions that are slightly more and slightly less dense. Under the influence of gravity, denser regions attracted matter, becoming even denser, forming galaxies and their clusters. And less dense areas were devastated, turning into voids. This is a process that has stretched over billions of years. Matter seemed to flow from future voids to their boundaries, where walls of galaxies were formed. Today, we see the result of this gravitational dance, a cosmic web where bright filaments of galaxies surround dark voids. The temperature inside the giant void is slightly different from the surrounding space. The cosmic background radiation left over from the Big Bang is a little colder here. This is due to the so-called integrated Sachs-Wolf effect. Photons passing through the void lose energy. To any hypothetical observer inside the giant void, the sky would look completely different than it does from Earth. Instead of thousands of stars in the Milky Way and a blurred band of our galaxy, he would see a virtually black sky with rare, barely discernible dots of distant galaxies on the event horizon. It would be true cosmic isolation, surrounded by emptiness for hundreds of millions of light years in any direction. Studying voids helps us understand the nature of dark energy, the mysterious force that accelerates the expansion of the universe. The voids expand faster than regions of high matter density, and this expansion could provide clues to how dark energy works. The giant void also poses philosophical questions for us. In an age when we are looking for extraterrestrial life and civilizations, voids remind us of the extent of cosmic loneliness. If an intelligent civilization arose in a galaxy inside such a void, it could consider itself the only one in the universe for thousands of years, simply because its nearest neighbors would be hundreds of millions of light years away. There are theories that voids could play a role in the future of the universe. As it expands, the voids will become larger and larger, and matter will become more and more concentrated in the walls between them. In the distant future, trillions of years from now, the universe may become like one giant void with rare islands of matter. Modern telescopes allow us to study the structure of the giant void in more and more detail. When astronomers point their instruments at this region of the sky, they use gravitational lensing techniques and analysis of the redshift of galaxies to build a three-dimensional map of this void. And each new observation reveals more and more amazing details of this cosmic architecture. One of the most intriguing features of voids is that they are not static. The giant void is slowly expanding, inflating like a giant bubble in the dough of the universe. This expansion is faster than the general expansion of space, because there is practically no matter inside the void that could slow down this movement with its gravity. In fact, voids are areas where dark energy manifests itself most clearly. What happens to the galaxies at the boundaries of the giant void? They exist in unique conditions. On one side, they are attracted by neighboring galaxies in the wall, creating dense clusters. On the other hand, from the side of the void, they are practically not affected by any gravity, only emptiness. This creates an asymmetric gravitational environment that affects their evolution and motion. Inside the void itself, the few galaxies that exist there have special characteristics. They are often smaller, contain less mass, and show signs of insulation from the cosmic streams of matter that feed galaxies in denser regions. These are galaxies frozen in time, slowly evolving in their solitude. Interestingly, voids can affect our observations of distant objects. When light from a very distant galaxy or quasar passes through the giant void, it undergoes certain changes. This is similar to how sound changes as it passes through different media. Astronomers take these effects into account when studying the most distant objects in the universe. There is a hypothesis that in the centers of some supervoids, special conditions may form for the emergence of wormholes or other exotic cosmic structures predicted by general relativity. Although this remains a purely theoretical assumption, the very idea that something unusual could lurk in the heart of the greatest emptiness is fascinating. The giant void also serves as a kind of cosmic laboratory to test our theories about the formation of the structure of the universe. Computer simulations of the evolution of the cosmos should reproduce not only regions with a high density of galaxies, but also voids of the correct size and shape. The correspondence between simulations and real-world observations confirms our model of cosmology. From the point of view of time cosmology, voids are time machines in reverse. If regions with a high density of matter evolve rapidly, where galaxies collide, stars are born and die intensively, then voids are regions of slow time, where cosmic evolution is slowed to a minimum. The galaxy at the center of the giant void may look the same as it did billions of years ago, preserved almost in pristine form. For future space travel, if it ever becomes possible on intergalactic scales, voids pose a particular challenge. Crossing the giant void would mean traveling through 1.3 billion light-years of near-absolute emptiness, with no refueling stations of stars, no resources, no intermediate goals. It would be the loneliest route imaginable. Some scientists speculate that the voids may hold clues to the nature of dark matter. Although there is little ordinary matter in the voids, dark matter should be present there as well, albeit in smaller quantities. Studying exactly how dark matter is distributed in voids can help us understand its properties and interaction with ordinary matter. There's also the intriguing possibility that the voids may be hiding relics of the early universe, objects or structures that formed in the first moments after the Big Bang and survived precisely because they happen to be in low-density regions where evolution is slowed down. When we talk about the size of the giant void, our minds are barely able to comprehend this magnitude. Let's try to imagine it differently. If our Milky Way galaxy were the size of a coin, then the giant void would be greater than the distance from Earth to the Moon. If we could travel at the speed of light, the fastest speed in our universe, it would take us 1.3 billion years to cross this void from edge to edge. During this time, eras would change on Earth, continents would move, species would evolve beyond recognition. The history of the discovery of voids is fascinating in itself. In the 1970s and 1980s, astronomers began conducting large-scale surveys of the sky, measuring distances to thousands of galaxies. When they started mapping these galaxies on three-dimensional maps, they expected to see a relatively uniform distribution with small clusters. Instead, they found something shocking. The universe has a cellular structure similar to foam or sponge, with giant voids between the walls of galaxies. The first major void to become widely known was the Boötes void, discovered in 1981. It was about 330 million light-years across, and it seemed incredibly huge at the time. But as our instruments and observation methods have improved, we have discovered even larger structures. The giant void in the constellation Coma Berenices turned out to be one of the most impressive examples of these cosmic voids. The constellation Coma Berenices is interesting in itself. It is a faint constellation in the northern hemisphere of the sky, named after the Egyptian Queen Berenice II. The astronomer Conan of Samos announced that the gods were so pleased with the gift that they placed their hair in the sky. Now, this constellation points us to one of the greatest voids in the universe, the irony of history, where the symbol of beauty points to a region of absolute absence. This constellation is also home to the Coma cluster, one of the closest rich clusters of galaxies to us, containing more than 1,000 known galaxies. The contrast is striking. In one area of the sky, we see an incredible concentration of matter, and next to it is the giant void, an area of almost complete absence. This clearly demonstrates the inhomogeneity of the structure of the universe. Modern cosmological models explain the formation of voids through a process called gravitational instability. In the early universe, about 380,000 years after the Big Bang, when it had cooled enough to form the first atoms, there were tiny fluctuations in density. These fluctuations, which may have occurred during the period of inflation, the ultra-rapid expansion of the universe in the first fractions of a second of its existence, became the seeds for the future structure. Regions with a slightly higher density began to attract matter. This process was self-reinforcing. The more matter collected, the stronger gravity became, the more matter was attracted. At the same time, regions with a slightly lower density lost matter, becoming even more empty. Hundreds of millions and billions of years later, these small differences have turned into a dramatic contrast between dense clusters of galaxies and huge voids. What is especially interesting is that this process continues now. The giant void not only exists, it is actively growing. Matter continues to flow from its inner regions to the boundaries, although the rate of this process slows down as the density inside the void becomes lower and lower. In hundreds of billions of years, the voids will become even larger and the concentration of matter at their boundaries will be even higher. Inside the giant void, there are interesting substructures. It is not a perfectly uniform void, but rather a hierarchy of smaller voids separated by thin filaments of several galaxies. This resembles a fractal structure, emptiness within emptiness within emptiness. Each level of this hierarchy was formed at different times and under different conditions, leaving a trace of cosmic history in the structure of the void. Galaxies that do exist inside the giant void are of particular interest to astronomers. They are often dwarf galaxies with a low rate of star formation. Isolated from the cosmic streams of gas and dark matter that feed galaxies in denser regions, these galaxies are slowly using up their gas reserves. Many of them have probably already passed the peak of their development billions of years ago and are now slowly fading away. But there are exceptions. Sometimes relatively bright, active galaxies are found inside voids. The origin of such galaxies remains a mystery. They may have been ejected into the void as a result of gravitational interactions at the boundary, similar to the way a rock shoots out of a slingshot. Or perhaps they formed in place from rare islands of matter that for some reason were not pulled into the void boundaries. Studies of the chemical composition of stars and galaxies inside voids show that they are often poorer in heavy elements than galaxies in dense regions. It makes sense. Heavy elements are produced in stars and spread out in supernova explosions. In isolated galaxies inside voids, this process is slower and the accumulation of heavy elements takes longer. The temperature anomalies in the giant void also tell a story. The cosmic microwave background radiation, a relic of the early universe, undergoes changes as it passes through the void. Photons fall into the gravitational potential at the entrance to the void and exit it at the exit. If the universe did not expand, these effects would cancel each other out. But due to the expansion of a universe and the presence of dark energy, there is a slight loss of energy, which makes the radiation a little colder. This effect, called the integrated Sachs-Wolf effect, allows us to detect voids without even observing the galaxy directly, but simply by measuring the temperature fluctuations of the background radiation. The giant void leaves its imprint as a cold spot on the map of the CMB, like a frozen trace in the history of light traveling for billions of years. If you imagine an intelligent civilization that arose on a planet in the galaxy at the center of the giant void, its perception of the universe would be radically different from ours. Their astronomers, looking through telescopes, would see an almost empty sky. The nearest galaxies would be hundreds of millions of light years away. They could have developed science and technology for thousands of years, sincerely believing that their galaxy was the only one in the universe. Only by creating extremely powerful telescopes would this hypothetical civilization be able to distinguish faint points of light at the very edge of the visible horizon, distant galaxies at the edges of the void. This discovery would have upended their understanding of the cosmos as radically as the discovery of other galaxies turned our understanding upside down in the 20th century. But for them, the shock would be even greater, from the complete certainty of absolute loneliness to the realization that there are trillions of other galaxies beyond the wall of emptiness. The philosophical implications of the existence of the giant void are profound. We live in an era when we can observe the deep structure of the universe, see its cosmic architecture. But this window of opportunity will not be open forever. Because of the accelerating expansion of the universe caused by dark energy, distant galaxies are moving away from us faster and faster. In trillions of years, galaxies outside our local group will disappear below the cosmological horizon, swept away by the expansion of space faster than the speed of light. A civilization that arose in that distant epoch would have seen a universe consisting of only a few nearby galaxies merged into one giant elliptical galaxy surrounded by absolute emptiness. They would have no way of knowing about the true nature of the universe, about billions of other galaxies, about the cosmic web of structure. For them, voids would not be the exception, but the norm. The entire universe would be one giant void with a tiny island of matter at the center. This makes you wonder, what can we ourselves not see due to the limitations of our position in time and space? What structures or phenomena exist beyond our cosmological horizon that we will never know about? The giant void reminds us that the universe is full of scales and structures that surpass our imagination. Modern sky surveys, such as the Sloan Digital Sky Survey, the Dark Energy Survey, and other projects, continue to map the distribution of galaxies with unprecedented accuracy. Each new survey reveals new details of the void structure, including the giant void. We find that the shape of the voids is not random. They tend to be elongated, following the general flow of matter in the cosmic web. The boundaries of the giant void are not abrupt, but gradual. The density of galaxies does not drop suddenly, but decreases smoothly as it moves from the dense walls to the center of the void. This creates a gravitational potential gradient that affects the motion of galaxies and the distribution of dark matter. The galaxies on the outer edges of the void move away from its center as if repelled by the void, when in fact they're simply more attracted by the dense regions outside. Interestingly, voids play an important role in cosmic streams, the large-scale motions of galaxies relative to the overall expansion of the universe. Our own local group of galaxies participates in such a flow, moving towards the Great Attractor and Shapley Cluster. Part of this movement is caused not only by the attraction of dense areas, but also by the repulsive effect of voids. It is as if we're sliding down a low-density hill to a high-density valley. The giant void also affects the propagation of cosmic rays and the intergalactic magnetic field. Although voids are mostly empty, they are not a perfect vacuum. They contain rarefied gas, mainly hydrogen and helium, with a density of perhaps 1 atom per few cubic meters. This is practically nothing compared to the density of air on Earth, where there are about 10 to the 19th power of molecules in a cubic centimeter, but it is still not an absolute void. This rarefied gas is heated to temperatures of millions of degrees by shock waves from supernova explosions at the void boundaries and radiation from quasars. Hot gas emits X-rays, although this radiation is extremely weak due to its low density. However, space X-ray telescopes can detect it, providing another way to study the structure of voids. The magnetic fields in the giant void are probably extremely weak, but they do exist. The origin of cosmic magnetic fields remains one of the mysteries of astrophysics. We detect magnetic fields in galaxies, in clusters of galaxies, even in intergalactic space. But how did these fields arise in the first place? Voids, as regions of least influence from galaxies and stars, may preserve traces of primordial magnetic fields that originated in the early universe, providing clues to this mystery. There's also an intriguing relationship between voids and neutrinos. These elusive particles, which have little to no interaction with matter, have been traveling freely through the universe since its birth. Relic neutrinos from the early universe should produce cosmic neutrino background radiation, similar to the microwave background radiation. Although this radiation has not yet been directly detected due to technical difficulties, it should theoretically exist. The distribution of these relic neutrinos should follow the structure of the distribution of matter, including the voids. In the giant void, the neutrino density should be below average, creating a kind of neutrino shadow. Future experiments to detect cosmic neutrinos could use voids as a testing ground to test our theories about the early universe. Gravitational waves, ripples in space-time predicted by Einstein and discovered in 2015, can also carry information about voids. When a gravitational wave from the merger of black holes or neutron stars passes through the giant void, it experiences certain effects due to the structure of space-time in this region. Although these effects are tiny, precise measurements could allow us to use gravitational waves as another tool to study the large-scale structure of the universe. The dark matter in the giant void presents a special mystery. We know that dark matter makes up about 85% of all matter in the universe, but we can't observe it directly. We see its effects through gravity, how it affects the motion of galaxies, how it bends the light of distant objects. In voids where ordinary matter is very scarce, dark matter should still be present, albeit in smaller amounts. Studying the distribution of dark matter in the giant void through gravitational lensing, the bending of light from distant galaxies, could help us understand the properties of this mysterious substance. If dark matter interacts with itself in a certain way, this should show up in its distribution within voids. Different theories predict different patterns, and observations can help us choose the right theory. There are also exotic theories suggesting that voids may not just be empty areas, but something more fundamental. Some versions of string theory predict the existence of extra dimensions of space, curled up to microscopic sizes. In rare cases, these dimensions can unfold at macroscopic scales, creating regions with different physical properties. Could voids be such areas? This is speculative, but not entirely impossible. Another intriguing hypothesis links voids to possible variations in fundamental physical constants. Some theorists suggest that in regions with extremely low matter and energy densities, fundamental constants, such as the speed of light, Planck's constant, or even the strength of the gravitational force, may have slightly different values. If so, then the giant void would be a natural laboratory for testing these radical ideas. Measuring spectral lines from rare hydrogen atoms inside the void and comparing them to lines from denser regions can reveal such differences. So far, all experiments show that the constants of physics are the same wherever we can measure them, but the accuracy of our measurements is constantly increasing, and who knows what we might discover in the future. The existence of the giant void also has implications for cosmological models of inflation. Inflationary theory suggests that in the first fraction of a second after the Big Bang, the universe experienced a period of exponentially rapid expansion, increasing in size by a fantastic factor in an unimaginably short time. This process stretched the quantum fluctuations to cosmic proportions, creating the seeds for the future structure. The size and shape of voids, including the giant void, carry information about these primordial fluctuations. Statistical analysis of the distribution of voids in the universe can help us understand the details of the inflationary period, how long it lasted, how fast it happened, what form of energy caused it. Each void is a window into the earliest moments of the universe, a frozen trail of events that occurred a fraction of a second after the birth of the cosmos. It is interesting to imagine how the giant void would be perceived by hypothetical travelers capable of crossing intergalactic distances. Entering this region of space, they would notice how the usual landmarks gradually disappear. Stars and galaxies are becoming increasingly rare, and the distances between them are increasing. Navigation is becoming increasingly difficult as the usual cosmic beacons, bright quasars, pulsars, characteristic clusters of galaxies, are left far behind. In the center of the giant void, travelers would find themselves in absolute isolation. Nearby galaxies would be hundreds of millions of light years away in all directions. Even moving at the speed of light, they would be cut off from the rest of the universe for geological epochs of time. It would be the greatest loneliness imaginable, surrounded by a void so vast that the light would not have time to cross it in a time comparable to the age of civilizations. But even in this emptiness, there would be no absolute silence. Space itself is filled with quantum fluctuations, virtual particles that constantly appear and disappear in a vacuum. According to quantum field theory, the vacuum is not empty, but boils with activity at the subatomic level. In the giant void, where there is no interference from matter and radiation, these quantum effects could be more pronounced. The Casimir effect, in which two closely spaced metal plates in a vacuum experience the force of attraction due to quantum fluctuations, could have interesting modifications under void conditions. The absence of ambient radiation and matter could amplify or alter this effect in ways that we are only beginning to explore theoretically. Voids also play a role in the distribution of baryonic matter in the universe. Baryons are protons and neutrons, the basic building blocks of atoms. Astronomers have long noticed a discrepancy between the amount of baryonic matter they can observe in stars and gas clouds and the total amount that should exist according to cosmological models. Where are the missing baryons hiding? It turns out that a significant part of them is located in hot, rarefied gas in voids and in the filaments of the cosmic web between galaxies. This gas is too hot to emit invisible light and too thin to be easily detected. But modern telescopes operating in ultraviolet and X-rays are starting to find this missing matter, and the giant void contains its fair share of these hidden baryons. The evolution of voids in time provides us with an opportunity to test our models of cosmic evolution. By comparing voids in the nearby universe with voids at high redshifts, as they were billions of years ago, we can trace how these structures grew and changed. Young voids are smaller and less empty. Older voids are larger and contain even less matter. This confirms our understanding of the gravitational evolution of the structure. The giant void may also contain traces of cosmic strings, if they exist. Cosmic strings are hypothetical one-dimensional defects in the fabric of space-time, possibly occurring in the early universe during phase transitions, similar to how cracks form in ice when water freezes. These strings would be incredibly thin, but would contain enormous mass and energy. If the cosmic strings were to pass through the giant void, they would leave characteristic traces in the distribution of matter and in the gravitational field. They could create small clusters of galaxies even inside the void, lined up along the string line. The search for such structures continues, and although there is no conclusive evidence of the existence of cosmic strings yet, voids remain one of the best places to look for them. The anthropic principle also finds interesting applications in the context of voids. This philosophical principle states that we observe the universe as it is, because only in such a universe could observers like us arise. If the structure of the universe were very different, for example, if it consisted mostly of voids with no dense regions, life could not arise because there would be no galaxies, stars, and planets. But the existence of voids as huge as the giant void is on the verge of being compatible with our cosmological models. If the voids were much larger or more numerous, it would indicate something fundamentally different in the nature of the universe. The fact that we see exactly the distribution of matter that we see with voids of this size and frequency agrees with our theories, but only barely. This reminds us that our understanding of the cosmos is still incomplete. Future space missions plan to study voids in unprecedented detail. The James Webb Space Telescope, already in orbit, can observe galaxies inside voids with never-before-seen clarity. Planned missions such as the Nancy Grace Roman Space Telescope and ground-based ultra-large telescopes will be able to conduct deep survey voids, cataloging every galaxy, every gas cloud. These observations will help us answer fundamental questions. How exactly were voids formed? Why do they have such sizes? What determines their shape? How do they interact with the surrounding structure? Each answer raises new questions, deepening our understanding of the cosmos. There's also the exciting prospect of finding relic objects from the early universe in voids. The first stars, called population 3 stars, were composed exclusively of hydrogen and helium, with no heavy elements. They were huge, bright, and short-lived. Most of them exploded as supernovae long ago, enriching the cosmos with heavy elements. But it is possible that some of them, by some chance, ended up in the areas that became voids, could have survived longer than usual or left behind special traces. Searching for these primordial stars or their remnants in the giant void would be one of the greatest discoveries in astronomy. These objects would carry information about the earliest stages of star formation in the universe, a period when the cosmos was just beginning to be illuminated by the first light after the dark ages that followed the era of recombination. Black holes can also lurk in the depths of the giant void. Not massive, supermassive black holes at the centers of galaxies, but wandering stellar mass black holes ejected from their parent galaxies by gravitational interactions. These solitary wanderers drift through the void, invisible and undetectable, unless they absorb a random gas cloud or pass in front of a distant star, creating a microlensing event. Theoretically, primordial black holes can also exist in voids, hypothetical black holes formed not from the collapse of stars, but directly from density fluctuations in the early universe. These objects could have any mass, from microscopic to stellar and larger. If they exist and form part of dark matter, as some theories suggest, then voids should contain a population of dark matter proportional to the total abundance of dark matter in these regions. The giant void is also a unique laboratory for studying the effects of general relativity on cosmological scales. In regions of low matter density, space-time is less curved than in dense regions. This curvature affects everything from the trajectories of light rays to the passage of time. The clock at the center of the giant void would run slightly faster than the clock in a dense cluster of galaxies because of the difference in gravitational potential. This effect is tiny, but it accumulates on cosmological timescales. A photon traveling through the void for hundreds of millions of years experiences slightly different conditions than a photon traveling through dense regions. These subtle differences can be measured and used to test the predictions of general relativity in regimes that are inaccessible under terrestrial or even circumstellar conditions. The entropy of the universe, a measure of its disorder, is also related to the existence of voids. According to the second law of thermodynamics, the entropy of a closed system always increases. The universe as a whole is evolving from a more orderly state to a more chaotic one. But the formation of structure, galaxies, stars, planets, seems to violate this principle, since matter is organized into ordered structures. The solution to this paradox lies in gravity. Although matter collects into galaxies and clusters, increasing the local order, the total entropy of the universe increases due to gravitational energy and radiation. Voids play a role in this process. They become low-entropy regions, while dense regions have high entropy. The giant void can be thought of as a giant reservoir of low entropy in the entropic economy of the universe. The fate of the giant void in the distant future of the universe is intriguing. According to current cosmological models based on dark energy observations, the universe will expand forever and at an accelerating rate. In hundreds of billions of years, the stars in all galaxies will burn out, leaving no gas to form new ones. Galaxies will turn into graveyards of white dwarfs, neutron stars, and black holes. But the voids will grow. They will become even bigger, even emptier. In trillions of years, the distances between galaxies will become so great that even neighboring galaxies will be beyond each other's cosmological horizon. In fact, the entire universe will become like one giant void with the rarest islands of matter, completely isolated from each other. In this distant epoch, sometimes called the epoch of degeneration, the giant void will be indistinguishable from the rest of the universe. The distinction between voids and dense regions will disappear, as the entire space will become almost completely empty. It's a grim picture of the heat death of the universe, but it's based on our best current observations and theories. However, there are alternative scenarios. If the nature of dark energy turns out to be different than we think, the fate of the universe could be different. Some models predict a big rip, in which the acceleration of expansion becomes so strong that it eventually tears apart not only galaxies and stars, but also atoms, and even space-time itself. In this scenario, the giant void would be one of the first places where these catastrophic processes would begin. Other models suggest a cyclical universe, where a period of expansion is followed by contraction, then a new Big Bang and new cycle. In such a model, structures like the giant void would be temporary. They exist in the current cycle, but will be destroyed and recreated in a new form in the next cycle. Philosophically, the giant void raises questions about the nature of existence and non-existence. What does it mean for space to be empty? Does emptiness exist as something, or is it simply the absence of something? In quantum mechanics and general relativity, even a vacuum has properties and structure. The void space of the void is not without meaning. It actively participates in cosmic dynamics. This is reminiscent of the ancient philosophical question about the nature of emptiness, which was discussed by Greek philosophers. Atomists like Democritus argued that only atoms and emptiness exist. Aristotle denied the possibility of true emptiness. Modern physics has shown that both sides were partially right. There is a space between particles of matter, but this space is not empty in the absolute sense. The giant void also serves as a reminder of the limits of human knowledge. Despite all our telescopes and theories, vast areas of space remain virtually unexplored. We know of the existence of a giant void, and can estimate its size and general properties, but detailed knowledge of what is going on in its depths remains limited. Each photon that reaches us from the direction of the void carries information, but this information is incomplete and requires interpretation. We build models, make assumptions, test hypotheses, but the full picture slips away. It's a good lesson in scientific humility. The universe is bigger and more complex than our understanding of it. It is also interesting to consider the giant void in the context of a multiverse, a hypothetical collection of many universes with different physical laws and constants. If a multiverse exists, then some universes may be dominated by voids, while others may be dominated by dense regions. Our universe has a certain balance between dense and empty regions, which may be necessary for the emergence of life. There are too many voids, and matter would be too thin for the formation of galaxies and stars. Too few voids, and all matter would collapse into massive black holes. The giant void and similar structures may be part of the fine-tuning that makes our universe habitable. This is speculative, but it shows how the study of emptiness can lead to deep questions about the nature of reality. The educational value of the giant void cannot be underestimated either. For astronomy and cosmology students, voids provide a concrete example of the large-scale structure of the universe. They show that the cosmos is not homogeneous, that it has an architecture and a hierarchy of scales. From planets to stars, from stars to galaxies, from galaxies to clusters and superclusters, and finally to voids and the cosmic web. The visualizations of the giant void, created from data from astronomical surveys, are impressive and inspiring. Seeing a three-dimensional map where each dot is a galaxy containing hundreds of billions of stars, and observing the vast void in the midst of this sea of light is an experience that changes perspective. We see our place in space. We understand the scale that surrounds us. For artists and science fiction writers, the giant void has become a source of inspiration. The idea of space so empty, so huge that even the light is lost in its depths, gives rise to images of cosmic horror and grandeur at the same time. It is the place where the laws of nature manifest themselves in their purest form, unclouded by the presence of matter. Perhaps the most important lesson that the giant void teaches us is that of contrasts. We value the light because we know the darkness. We understand the meaning of matter because we see emptiness. Our home on Earth, in the solar system, in the Milky Way galaxy, is surrounded by trillions of other galaxies, but they all exist against an even larger void. Every atom in our bodies was once part of the cosmic web of matter, slowly assembled by gravity. We are children of the dense regions of the universe, the product of billions of years of gravitational collapse and stellar evolution. But we exist in the context of voids, in a cosmos where emptiness dominates matter. The giant void in the constellation Coma Berenices will continue to expand, becoming larger and emptier. In billions of years, it will become even more impressive, even more frightening in its immensity. Astronomers of the future, if humanity or its descendants survive to see that time, will study it with technologies that we cannot imagine. Perhaps they will find answers to questions that we are just beginning to formulate. Perhaps they will discover phenomena that we do not even suspect exist. Or perhaps the mystery of the voids will be deeper than we think, and each answer will raise 10 new questions. But one thing remains unchanged. The giant void reminds us of the scale of the universe, of our tiny place in it, and At the same time, the incredible ability of the human mind to be aware of these scales, to study them, to try to understand them. We are standing on a small planet orbiting an ordinary star in an ordinary galaxy, but our minds are capable of encompassing structures billions of light years across. After all, the giant void is not just empty space. It is a monument of cosmic history, a record of its evolution recorded in the structure of the universe from the almost homogeneous state after the Big Bang to the complex web of matter and emptiness that we observe today. It is a window into the past, present, and future of space. When we look in the direction of the constellation Coma Berenices, we are looking at one of the most extreme manifestations of the structure of the universe. We see emptiness, but this emptiness is full of meaning. It tells the story of how gravity sculpted the cosmos for billions of years, how matter gathered in some places and left others, creating a contrast between light and dark, between being and non-being. And in this contrast, in this dance of matter and emptiness, we find beauty and meaning. The giant void is not just the absence of galaxies. This presence of something more fundamental, the very fabric of space-time, stretching over unimaginable distances, is a witness to a cosmic drama that has been unfolding for almost 14 billion years and will continue for trillions more years in the future. Thank you for being with us on the QUASARIA channel. We peered into one of the greatest voids of the universe and discovered that even in the absolute silence of space, there's a lot to tell. Keep looking up at the sky, asking questions and wondering. The universe is infinitely larger and more amazing than we can imagine, and each new discovery brings us closer to understanding our place in this majestic cosmos. See you again among the stars and emptiness of the infinite universe.